Good day everyone, I am Azarcon, and today's video, let's talk about Wilson's theorem. Wilson's theorem says if p is a prime number, then p minus 1 factorial is congruent to -1 mod p. To show that this is true, let's first expand out the left-hand side of this. P minus 1 factorial, if you write it out in full, it's p minus 1 times p minus 2 on and on times 3 times 2 times 1. The strategy, pair each number with its inverse, and because we're working mod p, the integers mod p are filled, which means other than 0. You can't divide by 0, so every non-zero number mod p has an inverse. So we should conceivably be able to pair every number with its inverse, but there are a few exemptions, and the exemptions are there are some numbers that are their own inverse. So let's see which ones those are. If a number is this own inverse, that means its solution to x squared is congruent to 1 mod p, because x times itself, x squared, it gives you 1. Now, we can solve this congruence. Let's just subtract 1 from both sides. That give us x squared minus 1 is congruent to 0 mod p. Now, we factor, that gives us x minus 1 times x plus 1 is congruent to 0 mod p. And now, we just solve this like we should in algebra. So now, set each factor equal to 0. So if x minus 1 is congruent to 0 mod p, means that it's congruent to 1 mod p. That's not a surprise, so 1 is its own inverse. Next, x plus 1 is congruent to 0 mod p, so 1 and p minus 1 are their own inverses. But every other number mod p can be paired with this inverse, and it'll be a different number. So now let's go back to p minus 1 factorial. So let's take in group 2 with its inverse, let's group 3 with its inverse, and so forth. And we're able to do this with every number, the exceptions being 1 and p minus 1. Now 2 times its inverse is 1, 3 times its inverse is 1, and so everything cancels out. And what we're left with is p minus 1, which is resolved just above, is the same thing as -1 mod p, and this proves that p minus 1 factorial is congruent to -1 mod p, and this is Wilson's theorem. And that's all. Thank you.